This video is 2014 higher level section A. Question A1. The drawing shows the projections of a set of soccer goals. A ball is positioned at P, so that's this point, for 2 penalty kicks during a World Cup game. The ball travels in a straight line and hits the net each time. The line PS, this one here, is in plan, shows the start of the flight path of the ball for the first penalty kick. The ball crosses the goal line at a height that is halfway through the ground, between the ground and the crossbar. Draw the projections of the full flight path. Part B of this question, similarly, the line PT, that's this one, which makes an angle of 15 degrees with the ground, shows the flight path of the ball for the second penalty kick. Draw the projections of the full flight path. So for this first one, we need to, for part A, find where the ball is going to cross the goal line. So we're told that that's above halfway. Sorry, it's at halfway. So we're going to extend, that means we're going to bisect this line. So at this point here is where the ball crosses the line. So drawing in the flight path of the ball, it's from point P through that point at the front of the goals, and it hits the goals here at the back. So it hits this point in the goals. We need to now locate that point in the elevation and the plan. So I'm going to extend the line, this point here on. So it's going to be in here somewhere. Don't know exactly where it's going to hit because it's on that slope. We know that it hits it at this height in the elevation. So it's up there somewhere. Again, not 100% sure where. So we need to take this point and find it in plan, and we're going to do that from the end view. So we're going to project this point from the plan, from the end view into the plan. That is the distance it is out from the back of the goals when it hits the back of the net. So that's this point. So our kick goes from here to here. And then just need to find that in the elevation. It's that point. This is the point in the elevation where it hits. So it's in horizontally across because it's the same height, and that's here. Now we just need to remember that we need to draw in the flight path. The full flight path in all of the views. So this here is this is point P in the elevation, and that's the flight path of the ball in the elevation. For part B of this question, again we've got a ball that's been kicked at the goals, and it's at 15 degrees, so it's going to come back this way and it's going to hit the back of the net. So it's coming back this far. Now what we need to do is we need to figure out what the height that is going to be. We can't find that in the end view because in the end view it's twisted away from us, so we're not looking straight in at it, so the angle won't be 15 degrees. So what we're going to do instead is draw that, rotate this down essentially in, so at the moment it's like tilted up like this. This is the flight path 15 degrees. We're going to flatten this down. That angle will be 15, and then we'll be able to measure the height off of that. So taking this distance here, perpendicular off of that, and then we can measure 15 degrees from P along the line T. I just need to extend this, just so that my protractor works properly. So 15 degrees is this angle. This is 15 degrees, and this here is the height that we're looking for. So that height there is the height that the ball is when it hits the back of the net. So So we can locate this now up in the elevation. So it hits the back of the net here, so it's going to be directly above it, and it is this height. This is the height that we need. That's the 15 degrees. So measuring that from the XY line, that gives us the height that the ball is when it hits the back of the net. This is the elevation of that line. And then to find the end view, the height is going to stay the same. It's touching off the back net, so our line is going to be going from here to here. So that completes this question, question A1. Question A2 is looking at truncated prisms. So the 3D graphic below shows a piece of playing equipment from a science museum, which includes a truncated hexagonal prism. The drawing on the right shows the incomplete projections of a similar hexagonal prism, which has been cut by the oblique plane VTH. So VTH. An auxiliary elevation is also given, so that's this. Complete the plan elevation of the cut prism, and then determine the true shape of the cut surface. So what we're going to do first is we've got our view up here where we can see that everything is the angle it's cut at and the point that it's cut at. So they've already given us these 2 points. Now we're looking for the top 2 up here. So they're from this point here, we're going to project those back. And it's along the top surface. So we're looking for the top edge. And that's, so we're going to work along these lines here. So what we've done is taken these points, projected them back and extended on those lines to intersect. That gives us those points. The other points then that we're looking for will be found by projecting from the plan to the elevation. Just going to extend these lines here because that's where the surface is going to be cut. So I'm going to take each point in turn. So I'm going to take this one. This is up on the top surface. So that's the point up there. This one here is also up on the top surface. That's that one. This point down here is not on the top surface, it's down lower. So that's this, the middle edge, and they've already given us the one there at the back. So these two are also in line with each other, so that's also a point down there. So that's this corner, which is there. So again, joining these up. And that almost does the elevation for us. Just a small bit of hidden detail to do in here. And some hidden detail to do down in the plan as well. So there's this bottom edge down here, so it's going to be hidden detail from this corner here until it disappears behind the visible line. So that corner again. That gives us that. So that's our elevation and plan complete. So that's part A. Part B is determine the true shape of the cut surface. For this we're going to use a rebatment, so we're going to take this shape and flatten it down that way. So each point on our hexagonal face is going to move perpendicular because it's rotating about HT. So I'm just going to take each point, project them out this way. And we already have all of these points up here, so what we're going to do now is rotate them around this point here on the x1, y1 line. So these distances, rotating these around until they're flat, so that'll be on the xy line, or on the x1, y1 line. These points here, and project them now back down parallel to HT. So this line here belongs to the top two, so that's this one and this one here. This next one is for the middle ones, so that's the middle height ones here and here. And then finally the two at the bottom where we have already. So that shape there is the true shape of the cut surface. Question A3 is based on conic sections. So the 3D graphic below shows a tangine, which is a type of clay oven frequently used in North African cooking. The drawing on the right shows the incomplete elevation. The upper lid is based on two semi-parabolas, so here and here, which are inscribed in rectangles, and the lower dish is based on a semi-ellipse. So we've got a partial ellipse down here. V1 and V2 are the vertices of the semi-parabola, here and here. P is a point on the semi-ellipse. Small portion of the two curves have already been drawn. Complete the elevation. Show clearly how the exact length of the base is obtained. So that's an important point that they've highlighted. So what we're going to do first is the parabolas. So we're going to measure the distances here. So they've given us one distance already, so we're just going to have to copy that, and you have to be very accurate with this. So copy this out as many times as it'll fit, and it should fit totally inside there, and it does. So copy the same, you don't need to copy distance on the side, we'll mirror it across afterwards. So doing the same thing up here, this distance is slightly different. And our distance there. So again, copying what they've already started for us. These lines here go parallel. I'm going to send them the whole way across because I'm going to use that in a minute. And there. And then these points join to the vertices. So labeling the points in the corner, this is 0, 1, 2, 3, and 4. 1, 2, 3, and 4. Where the 1s cross each other is a point on the curve. Same for the 2s and the 3s and the 4s they've already given us. Joining these points up, drawing the best curve that you can, gives us our parabola on the right hand side. So as I said a while ago, we're not going doing the exact same construction, we're going to mirror it across. So we've got an axis down the center and points on the curve. So we're just going to take each of those across the axis, like an axial symmetry from junior cycle. So distance from our axis to the point, same distance on the opposite side. Axis to point, same distance on the other side. So I'll do this for all of the points that we have. There and there. And again, best curve that we can that joins up all of these points. And that gives us our parabola on the other side. So that's the first half of part A done. The second half is we need to complete the rest of the ellipse. So we're using the auxiliary circles method for this. So I'm just going to do a random line here as well, and maybe one on this side. Now, what they've said that we need to find the exact point, so that exact point is specific. So what we're going to do is we're going to have to extend this on a little bit, and it's not just as straightforward as finding where the point is and find where it's going to come down and cut through it. that won't be the exact point. So what we're going to do is kind of reverse auxiliary circle. So if we look at this here, point P is a point on curve, we got a horizontal line coming out of it. That's the equivalent to this line here. So we've got a line coming from the center that goes through this point. So what we're going to do is we're going to take a line from the center here that's going to go through where that horizontal line cuts the minor auxiliary circle, and then that'll come horizontal and it'll keep going on and we'll come up and that'll find the point that we're looking for there. So doing that is from the center through where this point is here. So we've extended this horizontal line until it touches the minor auxiliary circle. Then I'm going to go perpendicular to the major axis, so that's going to give me this point. At this point here, that's the exact point from where it transitions from the ellipse to the base. Okay, so it's, I'll just change the color of that. So we've extended that on just a little bit more, and we got this line coming from the center through this point here. So that gives us that exact point. The other one then may not need. That gives us there, and so I can join these points up. That gives us that side of it. Mirroring this across the other side, there's an axis, so I'm just going to measure the distance from one side to the other. That'll give me the exact point for where it transitions on this side, and then auxiliary circles method for the rest of it. Or you can mirror it across as well. So point on the curve, and here as well. And this is the base. So that completes that bottom part. Just darkening this again. So just again on this point, we're kind of doing what they have done up here. So point from the center out through this point here where that horizontal line intersects the minor auxiliary circle. That's this blue line coming down this way. Where that cuts the major auxiliary circle, we're going to go perpendicular to the major axis. That's already coming across here, so that gives us this exact point where that transitions, where it changes from the base to the horizontal line. So the final part of this then is to draw a tangent to the curve. So a tangent is going at point P. Draw a tangent, we need our focal points. So we're going to measure half the major axis. So that's from the center out to this point here. From the end of the minor axis, which we have, which is here, I'm going to swing an arc so that it cuts the major axis in two places. That'll be F and F1. And we're going to join the two focal points to point P, and I'll extend through. So focal point to point P and extend through. And then that gives us an angle. So we got two angles. We got this one, which if we bisect will give us a normal. We're going to bisect the other one, which will give us our tangent. So this point here is a point on the bisector, which is a point on the tangent. So there's our tangent to point P. Final question on this paper is a perspective question. So the drawing on the right shows a partially completed perspective projection of a tennis court. Part A, the position of one of the vanishing points VP2 is shown. Locate the other vanishing point. Part B, complete the perspective projection of the tennis court and the net. And then part C is determine the true height of the net. So for this, anytime we're trying to find a vanishing point, we're always going parallel to one of the edges of our object. So the extreme edge, so this is one, they've already gave us the other one, from the spectator. So this line here is parallel to the edge of this. And then that's going to be projected down onto the horizon line. That's this one coming down here. This is VP1 that I'm looking for. So that completes part A. Part B is to complete the perspective projection of the tennis court. So we're going to be bringing points from each different points up here to the spectator, and where they cross the picture plane are projected down into the perspective view. Now this corner here is this one of our drawing, and this is along this edge, so that's going to join back to the vanishing point on the left. So this is a line going to be back here. We need to work out where it disappears, and we'll do that in a minute. This is going to come back this way as well, so back along there somewhere. So that's this edge and this edge drawn. Going to find the line at the back now, so we're going to take this corner, join it to the spectator where it passes through the picture plane. I take this line into the perspective, and that gives me this point down here. This point I'm going to join back to the other vanishing point, so VP2, and it's going to give me this line here, so the back of the tennis court. So what I'm going to find now next is this point here, this line. So again, joining this point to the spectator, crosses the picture plane at this point, and then that's projected down onto the ground. So that's this corner down here. Again, going to join that back to vanishing point 2, because that'll give me this line. That line's parallel to this edge, so that's why that's going to this vanishing point. That goes there. Same thing for this side, so this corner to the spectator. So this will come down along again, and that goes to that corner. Again, back to the vanishing point 2. That gives us this line. And all we need to do now is, so I just need the line down through the middle. So again, same idea, line to the spectator, where it crosses the picture plane, project into the perspective view. It crosses, that's this line, that crosses this line, so that's this point on the drawing. I'm going to join that back to vanishing point 1, and it's going to go back that far. So that gives me that line there in the center. And that completes part B of this question. The final part of this question is to determine the true height of the net. So the only way you can see the true height of something is if it's on the picture plane. So we need to project stuff. We can either project it down here onto the picture plane, which is a bit unnecessary at the moment. So what we can do is, if it's on the ground line, then we can also see the true height of it. This is the net, so I'm going to project from the vanishing point 2 along the net, taking the bottom and top lines down along this way, and the top one as well. That's this line. So then marking our vertical, so parallel to all the other lines. That is the height that we're looking for. And then that completes this paper.